Hello and good day everyone, my name is Ron and let us answer some separation processes problems. So this problem is a reference to problem 22.1-5, an example of transport processes and separation processes principles 5th edition book by Jean Copley, Hercel, and Lepek. So this problem here is a modification of the reference problem and it is stated as follows. It is desired to absorb 97% of the acetone in a gas containing 5% mole of acetone in air in a countercurrent stage tower. The total inlet gas flow to the tower is 50 kilomoles per hour, and the total inlet pure water flow to be used to absorb the acetone is 108 kilomoles of water per hour. The process is to operate isothermally at 25 degrees Celsius and a total pressure of 101.325 kilopascals using Raoult's law. Find the theoretical number of stages. So here is the given diagram with the corresponding data. So here, as you can see here, pure water, the liquid inlet, gas inlet, and it must be that the gas enters from bottom to bottom and exits at the top, and liquid enters at the top and exits the bottom. And the absorbent is pure liquid water, the solute is gaseous acetone, and the solvent is air. And the pressure and temperature as follows. And what we need to find is the capital N, or the number of theoretical stages needed for this separation process. So before anything else, normally I would solve using DWSim or simulator and compare it with my hand calculations to prove the worthiness of DWSim. But in this case, I would solve it first using hand calculations before DWSim, because one of the DWSim's unique properties is that in order for this to be solved, we need to know the stages to be considered. And so we still don't know the stages to be considered, and that is what we want to know. What I did is I first hand calculated the number of stages and used that value to the DWSim and compare the values of the DWSim and the hand calculations all together. And in this case, I would not only use the analytical method, I will also use the graphical method. Also take note that there are different types of methods to solve this problem in terms of stages. One is the analytical method by Kramser equation, and the other is a graphical method used by the McCabe-Thiele method. So I will use both, and this is how the video will be solved. I will solve it using analytical equation and find the minimum stages. Then I'll use that minimum stage value for the DWSim. Then I'll compare the DWSim and hand calculations using graphical method comparison. So with that all said and done, let us begin. So the required is the number of theoretical stages. So what we need to do is to do a pre-solution for equilibrium, find the equilibrium relation of acetone A. If you have solutions thermodynamics under your belt, you might be familiar with this certain type of equation. So this is, in creating an equilibrium equation of a certain component, you just need to equate the liquid phase of its liquid phase and its gaseous phase. So its gaseous phase has this form and its liquid phase has this form. Since under Raoult's law conditions, this component is equal to 1. I think this is fugacity coefficient. No, this is fugacity. And this one is the activity coefficient at liquid phase, and this is also equal to 1 due to Raoult's law. And this is the fugacity coefficient. The fugacity coefficient under Raoult's law also is equated to saturation pressure, and the pressure here is equated to total pressure. And deriving the equation, we would have this formula, where it is similar in the form of a line equation where y equals xm, and m is the slope of the line. So we already have the total pressure. We need the saturation pressure of acetone. So how do we do that? We use the Antoine correlation. And how do we find the values of the Antoine correlation? I took it from the table B.2 of the Introduction to Thermodynamics CHE 8th edition by Smith, Van Ness, Abbott, and Swihart. So using the saturation pressure Antoine correlation formula and the values from the book of SVA 8th edition, CHE Thermodynamics, I calculated a saturation pressure of acetone to be 30.6592 kilopascals. Then I used this value and substituted this value, since I already know the total pressure as earlier in the given, which is 101.325 kilopascal. This is my equilibrium relation line. Afterwards, I need to find the components of each of the streams of the inlet gas, outlet gas, inlet liquid, outlet liquid. Baliktad. Opposite. So gas inlet, gas outlet, liquid inlet, liquid outlet. So finding the amount of acetone liquid outlet, since this problem stated that 97% of the acetone will be absorbed, meaning that 97% of the feed of the acetone in the feed, which is the only acetone present in the feed, is in the gas. That means 97% of the gaseous acetone would be present in the liquid outlet. Doing this formula, we have this parameter, this formula. And since we don't know the amount of liquid going out or the outlet liquid, don't worry, because we can solve it by further calculation. So we need to find the moles of inert water. Since we will assume that water is inert, meaning it will not react in any way between air and acetone. It will act just as a carrier. And another thing to note is, to simplify this explanation, how much water going in is also the same as the amount of water going out in its liquid phase. It doesn't go to gas phase, it doesn't react with air, it doesn't react with acetone. It is liquid water through and through. Which essentially means, logically speaking, that liquid inlet of water is also equal to the liquid outlet in terms of water. So that's why there's an L apostrophe here. L apostrophe refers to the inert material, which is essentially water in liquid form. So this is a mole ratio formula, and to do so, we need to find out what is the inlet liquid and the mole fraction of a component. Since there's no acetone in pure water, as I said, pure, this may equate to 0, and from the given, the amount of water going in is 108 kilomoles per hour. That means the amount of inert water is also 108 kilomoles per hour. Then finding the liquid outlet, this following the same formula as this one earlier. However, this is in terms of the outlet conditions. Since we already know the inert amount of water going out and in, and we also know xn, which is this one earlier, substituting it, and we have one unknown and one equation. I calculated that the outlet liquid components exit the stream at 110.425 kilomoles per hour. So now let's discuss in terms of gas. So since there's 97% of the acetone in the feed in the liquid, from the gaseous feed in the liquid, that means the rest of the 3% acetone is still retaining in its still gaseous form. Meaning that 3% of the gaseous acetone is exiting as in the gas outlet. So doing so, substituting values, we will have this formula, and it's essentially the same procedure as earlier, finding the mole ratio of the finding inert air. So if we have inert air, then we will also assume that the air is inert water earlier. We will also assume that the air is inert in the gas form, meaning again that the air will not react with acetone or water in any reaction whatsoever. It will just act as a carrier or a conduit. With that said, substituting this mole ratio equation for the air component in terms of inlet, we would have an inert air of 47.5 kilomoles per hour. Then using the same equation, such that this is for the outlet conditions, and since we do not know the amount of gas going out, but we know how much air is going in, inert air going in, essentially meaning going out, V apostrophe, and we know Y1. Y1 is this formula. This means that the amount of gas exiting the streams or exiting the system is 47.575 kilomoles per hour. Then we need to find the mole ratios using this formula at gas inlet and gas outlet, liquid inlet, and liquid outlet. This mole ratios is all with respect to the component being transferred, which is acetone. And I put them at fraction form so that the result to be hand calculated is still as accurate as possible numerically. So why do we need to do this? Because I want to double check and make sure if these values that I calculated earlier are proven by balance. So I did a component balance between with respect to acetone. So the acetone going in equals to the acetone going out. So this is the amount of acetone in the liquid, the amount of acetone in the gas, and the amount of acetone in the liquid going out, and the amount of acetone in the gas going out. So substituting all values stated here and the values calculated earlier, in the left side, the amount of acetone going in is this value. And this one, the amount of acetone going out is also this value. If these values are both the same, this means that it is balanced and proven by material balance, and it does not go against the law of conservation of mass. So this means, essentially meaning that all values calculated are proven mathematically and logically. With that in mind, we can now solve for the number of stages. To do that, I will use an analytical solution, as said earlier. So finding the absorption factor at the top requires this formula. So the absorption factor at the top is the molar flow rate times over the M. M is what I calculated earlier, which is this one. The ratio equilibrium mole the equilibrium slope constant here of Raoult's law. I'll just call it Raoult's equilibrium constant. Afterwards, I calculated the absorption factor of the top using this formula, 7.5020. The absorption factor at the bottom is 7.2984, and finding the geometric average of both is the absorption factor at the entirety, or average absorption factor, the entirety of the absorption column is 7.3994. Then, in order to find the theoretical number of stages for absorption columns, I would use the Kremser equation for absorption. The Kremser equation is an analytical shortcut solution in order to find the number of stages without having too much effort. So, using the Kremser equation and substituting all values that I have recently calculated, I discovered that the amount of stages needed is 1.6571 stages. Rather than just rounding it down, it makes it unrealistic. We should round it up further so that the estimate would still satisfy the specified processes stated earlier. Hence why, rounding up this value, I would approximate that the problem would require 2 stages in order to complete these certain separation processes. Then with that in mind, with that specification of handheld calculations completed, let us now go to the DWSIM simulation and procedure. To start with simulating in DWSIM, we need to create our new process model. So here, we'll click here, create new, and we'll wait for it to load. Then we'll do the general procedure of DWSIM. Go to introduction, press next. The compounds, so going back to the problem, the compounds are water, acetone, and air. So we'll click here, water, enter, acetone, and air. So only water, acetone, and air are in the mixture. Are only the components considered in this problem. So we'll click here next. Then the property packages. Since we'll just use Raoult's law here, we'll just find Raoult's law. Add here. Then the system of units, will have our own customizable system of units. So the molar flow rate is kilomoles per hour. So kilomoles per hour. The pressure is, there is no pressure specified. There is kilopascals, and there is a temperature specified, which is, we'll use Celsius to be easy, 25°C, and then afterwards, that's it. So we'll finish. Then, since we're dealing with absorption, so we will use the cape open. But before we can use the cape open, we must prepare our respective streams, material streams. So the liquid inlet, the gas inlet, the liquid outlet, and the gas outlet. So in absorption, it's always that the liquid flows from top to bottom. So this must be we'll change it to liquid inlet, and the gas must flow from bottom to top. Since it's gas, it flows upwards. So we'll go here, gas is gas inlet, and here, by logic, this means this is a gas inlet and gas outlet. So gas outlet, and here this is a liquid outlet. Okay, so let's specify our feed. So in the liquid inlet, it's only pure water. So this means that compound wise, only water is there, mole fraction wise. So put here 1, 0, and 0. Click accept. Stream conditions. So we said that the temperature is 25 Celsius. We don't need to change that anymore. Pressure is 101.325 kilopascal. So we don't need to change that anymore. So essentially, we just need to change the molar flow rate, which is 108 kilomoles per hour. So 108 kilomoles per hour. Okay. Then for the gas inlet, it's 5% ammonia and 95% mole of inerts or inert air. So this means that the water must be 0 in mole fraction. Acetone is 0. Acetone. Apologies. This is supposed to be, I forgot to change the figure here. This is supposed to be acetone, not ammonia. Sorry for that. This is supposed to be 5% mole of acetone. So 0.05% mole of acetone, then 95% mole of inert air. So to check if it's 1, it is correct mathematically. And the pressure, temperature, and molar flow rate. So the molar flow rate is 50 kilomoles per hour. So put here 50. Alright, then the gas outlet and the gas inlet will not change anything. We just need to rename it, since we will, through the column is where it will be solved properly. Afterwards, we'll get the Cape unit operation, drag and drop, and wait for further details. Click OK, and this column will appear. And we'll open the Cape editor in order to get more details. So the unit name is absorption, and the operation is a simple absorber and stripper, and the following details will be further discussed or edited in the corresponding editor pages. So we'll just wait for a few seconds, and the editor page is here. So we will uncheck this Cape Open Properties, because the Cape Open Properties has its own property package. And since we use Route's law, that means we don't need to use the property package of Cape Open. So we'll just uncheck this. And we don't need to expose the energy ports anymore, since we only need to find in terms of mass transfer. So there's no need for energy ports, since, again, as I said, title, components, none, operation, simple absorber stripper, number of stages. So this is where, this is the reason why I need to calculate the problem by hand first, before the simulation. So by hand calculation, I calculated that the number of stages needed is 1.6571. So I put here 1.6571, and it will adapt to 1. However, that's not realistic, so I'll change it to 2. This is the problem sometimes with Cape Open. It rounds down the decimal values, and it only accepts whole number. Hence why, to truly be accurate in the results, I used 2 stages. I used the approximate value I calculated in hand calculations, and used 2 stages here. So feed stage is 1. Feed stage is 1. Some absorber stripper, and 2. So feed is 1 and feed is 2. So this is the liquid outlet and the liquid inlet, liquid inlet and the gas inlet. Okay. Afterwards, this is the operation. The properties, we specify this Route's law. Vapor pressure is Antoine, and the enthalpy is ideal. Alright. Reactions, none. Feeds, none. Specifications, none. Nothing to change here. Constant pressure, 11325 kilopascal. 11325 pascals. So in terms of kilopascals, it is 101.325. So there's nothing to change here. There's nothing needed to change, since kPa in Pascal it's 11325, and this is 11325 Pascal. Heaters, coolers, no need. Efficiencies, no need. Column specs, no need. And results, not yet. So we'll just save it here. Press X. We'll save the current. We'll save the current specifications, and now we are now able to connect all our needed parameters. So remember, the first stage is always at the top, and the last stage is always at the bottom. So the feed going in the first stage is actually the liquid always. So we'll put here at the first stage, or stage 1, liquid inlet. And then the first stage, then the bottom stage is the gas inlet. Okay. Afterwards, we'll click the outlet stream. The top product is the gas, since gas flows from bottom to top. Gas outlet. And then the bottom product, liquid flows from top to bottom. So liquid outlet. Since they perform countercurrently, so it's like this visually. So if this is liquid, liquid and gas, like this or like this. So afterwards, since we already edited the details earlier, we'll just solve it. And we'll just wait for a few seconds. And finally, this is the result. So we need to find the number of stages. So we need to go to editor. Go back again to the editor. Look at the McCabe-Thiele graph. And actually, let's just look at the results. And the result is that the outlet's specifications. So though you can see it here, it's easier to just check it in the DWSIM procedure itself. So this is the gas outlet. The gas outlet is smaller flow 49.0984, and the compound is 0.0346, 0.000, and 0.96 respectively. The liquid outlet, the molar flow is 108.902, compounds are 0.9760, 0.0225, and 0.00133. So how do we compare? How would we be able to compare the values in the calculated and the simulated? Since we assume that the number of stages here is 2, then what is our source of comparison if we just assume the number of theoretical stages? We can compare the outlet properties. Since earlier in the hand calculation, we also calculated the outlet properties using hand simulation, hand calculations, and balancing, and the simulator also has its own version of the outlet streams composition and flow rates. We can compare these two and try to find a conclusive conclusion on what does the data actually represent. Alright, so this is what I did. So the percent difference calculation. So from DWSIM, since I assumed that, I inputted it to be 2 for theoretical stages rather than this decimal hand calculation, due to the fact that, again, the Cape Open only requires values that are in whole number variation. So for the liquid mole outlet, it's supposed to be liquid outlet, it's 108.902. For the gas, it's around 49.09484. Then for the acetone in the gas, it's 0.0008, and the acetone in the compound is 0.0226. So this is the DWSIM values, and these are my hand calculation values. To double check, my hand calculation is 110.425. Alright, so these are my hand calculation values and DWSIM values. Then I tried to calculate the percent difference between the two, and these are the percent difference values. So as you can see, for the liquid mole outlet, it's all, and gas and acetone, they are below 5% difference. However, for the acetone mole fraction in gas outlet, it's actually quite high, 66.66%. So I can conclude that the simulator and my hand calculations are accurate enough to be good estimates of the problem's required solution. And the reason for such a large percent difference between the two is because Cape Open, again, does not allow incremental stages to be inputted as seen earlier as here, only by using whole numbers. So this is how we can compare between the values of DWSIM and hand calculations. So hand calculation, I use the Kremser equation, and DWSIM, I use the Cape Open. And as promised, I will also do a comparison of graphical relationships or graphical components. So using the McCabe-Thiele, so if the analytical solution for the absorption is Kremser equation, for the graphical solution, it uses McCabe-Thiele method. So how do we do the McCabe-Thiele method? Simply put, the procedure is very simple. You need to plot the liquid mole fraction and the gas mole fraction. So remember our equilibrium line calculated earlier, derived earlier, which is this one. this is our equilibrium relation line. And I use this to plot the equilibrium line needed for the graphical solution. So the blue represents the equilibrium line. And what is this black line, if you may say so? This is the operating line. So this operating line represents the mole fraction of acetone and the liquid and the outlet at the top and the bottom respectively. So this is actually at the top of the absorber, and this is the bottom of the absorber. So how do we find it graphically? So using my hand solution values, using the operating points hand solution wise, I calculated, graphically I can see that, okay, for graphical method, you start first at the top portion of the operating point or operating line, then project it horizontally to the equilibrium line. As it hits the equilibrium line, project it vertically until it hits the operating line. Keep doing it until this cascading line or stair line overpasses the operating line. And how do we know the amount of stages from this? Well, how many times it hits the equilibrium line is equating the amount of stages theoretically. So since in this graph, it hits the equilibrium line 2 times before it bypasses the operating line, that means that using in my hand solution values, operating equilibrium lines, it requires 2 theoretical stages. And going back to my Kramser equation, also approximately 2 stages analytically and proven graphically on my hand solution values. But what about if we use the DWSIM values? So the equilibrium line stays the same, but the operating line is a bit different. Since the operating line is at these values, then it has a different form compared to this. So this is my hand solution operating line, and this is the DWSIM values operating line. But if you can see here, as we do the same procedure, we're projecting it horizontally and vertically as it hits the equilibrium line, it also approximates to 2 theoretical stages. So graphically speaking, they estimate the same theoretical number of stages, which is 2. In conclusion, I have proven that in hand calculations, both graphical and analytically equation-wise, using DWSIM also shows that the answers for both hand calculation and simulator are very, very close enough. Therefore, I also conclude that for this separation to work, it requires a theoretical number of stages of 2. Again, my name is Dayap. Thank you for watching. Good day.